Hello, this is a presentation of a survey paper on point cloud completion published on the Journal of IEEE Transactions on Visualization and Computer Graphics, TVCG. In this paper, we introduce the task of point cloud completion and classify completion methods by their inputs, outputs, and technical approaches. We list the datasets, evaluation metrics, and network architectures often used for the task. We discuss technical challenges in the field and point out future research directions. Point clouds are a collection of 3D coordinate points that represent 3D shapes. Point clouds can be produced by active or passive acquisition methods. Active acquisition refers to the capturing of point clouds directly by sensors like LiDAR and Kinet, whereas passive acquisition derives point clouds from other data types like images and meshes by using techniques like structure from motion or multi-stereo imaging. Point cloud completion has many real-world applications in fields such as robotics, augmented reality, autonomous driving, etc. Most of these applications use point clouds acquired by active acquisition methods. However, due to factors such as self and object occlusions, viewing angles, sensor quality, environmental conditions, and measurement errors, most of the resulting point clouds are sparse, incomplete, and noisy. So, we use point cloud completion to estimate the missing parts of the point cloud. There is a lot of work in the area of point cloud completion. Here is how we define the scope for our literature survey. Point cloud completion is part of the larger field of shape completion. Shape completion infers the complete geometric shape of an object or a scene from a partial input of any 3D data type, like mesh, voxels, or point clouds. Shape completion is classified into object completion, semantic scene completion, and semantic instance completion. Object completion completes the missing part of a single object. Semantic scene completion completes the missing part of a scene. Semantic instant completion detects individual instances in a scene or object parts based on their semantic information. In this survey, we exclusively focus on object completion of point cloud partials. Now we discuss the classification of point cloud completion methods. Based on the type of inputs, we classify existing works in completion to unimodal and multimodal groups. Most early works use unimodal inputs of a single partial point cloud. Completion methods that rely on symmetric cues for completion may require their inputs to have specific geometric features like symmetry and simple shapes like rectangles and cylinders. Deep learning-based completion methods do not have such requirements. There are a few papers that use two partial inputs of the same object as complementary inputs. Many recent works use multimodal inputs for improved completion results. These multimodal inputs can be a combination of partial point clouds with single view RGB images or with shape prior information like object labels or semantic data from a point clouds database. Based on the number of outputs, existing completion works are also divided into unimodal and multimodal groups. Unimodal outputs produced only a single output, which is either a fully predicted complete point cloud or the predicted missing part of the partial input. Multimodal outputs can be either multiple complete predictions from a single partial input or a complete predicted point cloud with an explanation element, such as an uncertainty map. Approach, we divide completion methods into traditional and learning-based groups. The traditional approach optimizes the parameters of shape models to fit the partial inputs, whereas the learning-based approach makes use of deep learning neural networks to predict the complete point cloud. Traditional approaches can be divided into these four groups. Interpolation-based methods fill holes locally by smooth interpolation, constructing new data points based on known data. Matching patch searching methods find points or patches that are similar to the missing parts of the input. Then they duplicate the patches and fill the holes with the copied patches. However, a matching patch may not always be found. Example-based methods complete the shapes by matching the partial inputs with template shape models from a large shape database. Although these models can complete larger missing regions than interpolation and matching patch-based methods, if corresponding shape is not found in the template dataset, that could lead to misleading completion results. Geometry-based methods complete shapes by using geometry cues like structural property, symmetry, and regularity. However, they may not perform well for irregularly shaped objects. Learning-based approaches complete shapes by directly mapping the partial input to a complete output by using neural networks. These approaches don't make prior assumptions about the shape of the object unless they are explicitly trained to do so. There are three types of learning-based approaches: supervised, weakly supervised, and unsupervised methods. Supervised methods rely on the availability of paired training data for completing tasks. Paired training data refers to a collection of partial point clouds and their corresponding complete point clouds. Weakly supervised methods use information from a small set of input-output paired data and apply it to a larger part of the data, which only consists of unpaired inputs without labels. Unsupervised methods don't require paired data, but they take a longer time to train. Papers implementing these methods are discussed in the survey paper in detail. Discuss datasets and evaluation metrics in point cloud completion. It is mainly learning-based approaches that require datasets for training purposes. The most common 3D dataset used for completion is ShapeNet dataset. ShapeNet is a large-scale repository for 3D CAD models. Researchers in point cloud completion derive point cloud completion datasets by uniformly sampling points from the surface of the 3D CAD models. The PCN dataset, Completion 3D, Multiview Partial Point Cloud MVP dataset, ShapeNet 3455 datasets are examples of completion datasets derived from ShapeNet. Another popular choice is the ModelNet dataset. Some more recent works have been seen using Matterport 3D, ScanNet, Kitty, and NewScene's datasets. When it comes to evaluation metrics, we found that traditional methods usually use qualitative visual evaluation to assess the results of their completion. The evaluation is mostly subjective and can be dependent on human perception whenever quantitative measures are not present. Learning-based methods, however, mostly use quantitative evaluation measures. The most popular ones are Earth Movers Distance EMD, Comfort Distance CD, and F-score. Earth Movers Distance EMD evaluates the dissimilarity between 2 points by finding a bijection that minimizes the average distance between corresponding points in the partial and complete point clouds. It requires the number of points in the partial and complete point clouds to be equal. Comfort distance represents the average distance of the closest points between 2 point clouds. It is the most popular metric in completion. However, it can be insensitive to disparity in local density distribution and can be sensitive to outliers. An improved version of the comfort distance is the density hour comfort distance DCD. For real-world datasets that do not have ground truth point clouds, maximum mean discrepancy, MMD, fidelity, and consistency are used. MMD calculates comfort distance between output and a shape from a synthetic dataset that most resembles the real-world output. Fidelity measures the preservation of the input data, and consistency estimates how consistent the model's outputs are against variations in the input. Now we briefly summarize the network architectures often used in completion. Convolution-based methods transform point clouds to voxels or 3D grids and then use 3D convolution to complete the shape. But this voxelization process could lead to loss of local geometric information and can be computationally costly. Point-based methods process raw point cloud inputs directly through PointNet or PointNet++ backbones by using multi-layer perceptron. Point-based networks are the most common architectures in completion. Graph-based networks treat points in point clouds as vertices of graphs and generate edges between neighboring points. Generative model-based networks generate data based on the data they are trained on. They are classified into generative adversarial network GANs, variational autoencoders VAEs, and diffusion models. Transformer-based networks make use of transformers for inferring local and global spatial relations in the point cloud. Completion networks that use different approach are put in the other networks group. This network-based classification is discussed in detail in the survey by Fay et al. Cited at the bottom of the page and in our survey. Here we discuss the technical challenges in the field of point cloud completion that were identified during our survey. These challenges arise from the properties of point clouds and are as grouped as follows: noise and outliers, unordered structure, lack of paired data, density, and effective feature representation. Point cloud data of real-world objects acquired from sensors and cameras are often noisy and full of outliers. Current completion works assume clean point clouds and avoid the noise issue altogether. This approach affects the performance of the completion algorithms on real-world datasets. The limited works that try to deal with noise in point cloud completion are discussed in detail in our survey. The second challenge is unordered structure. Point clouds differ from other 3D representation formats such as RGBD image meshes and volumetric grids because point clouds are irregular and unordered. Thus, they cannot be directly processed by convolutional neural networks. Researchers approach this problem in two ways. The first is by restructuring the point clouds into 3D grids or voxels and by using 3D convolutions for the completion and inference. The other method is by using permutation invariant networks like PointNet and PointNet++ to directly process the point clouds, extract features, and complete them. While the former method is more robust to noise than the latter, it also tends to be highly costly in computation power. The third challenge is lack of pair data. It's very difficult to capture clean and complete point cloud data that can serve as ground truths for supervised learning-based point cloud completion algorithms. State-of-the-art completion algorithms use synthetic point cloud pair datasets for completion. The first partial point clouds are made by directly cropping the complete point cloud. Later, researchers use back projection of 2.5D DIPS images into 3D point clouds. This effectively simulates the regions of point clouds that would be most likely missing if the point clouds were directly acquired from scanners. However, this doesn't account for outliers and noise in real scans, so synthetic point clouds cannot represent real-world data. The fourth challenge is density. In this context, density refers to the number of points available per unit area. Point clouds are captured at different densities based on the sensors and the environment. Real-world scans often consist of millions and billions of points. This requires an incredible amount of computation power to process, which we don't have. Most state-of-the-art algorithms use downsampling and reduce the need for subsequent convolution layers. However, this leads to loss of information. In terms of output, state-of-the-art completion algorithms produce point clouds up to 16,378 points. This is large compared to past works. However, it is nowhere near the number of points in real-world point clouds. Loss of local details is one of the primary challenges researchers in point cloud completion encounter. Thus, they have come up with several techniques to effectively represent local features, and some of which are listed here. Parametric surface features techniques map sets of squares to the 3D shaped surface and encode them with the point cloud latent features, as was first shown by AlexNet. Intermediate representations encode local structure and positional details for an enhanced feature representation. These can come in the form of patches, seeds, skeletons, spots, etc. Some methods blend the partial input with the predicted output in an effort to preserve local features in the input. Some works like PMPNet reformulate completion as a deformation problem in order to preserve local features. A few other methods try to extract local and global features simultaneously. The first approach is by using enhanced network design as a means. This refers to the use of mechanisms like self and cross attention, soft pooling, neighborhood pooling, etc. Networks like PFNet apply multi-level feature extraction for better completion results. Some methods use multi-pass feature extractions that use separate paths for global and local features. After identifying the different challenges in the field and techniques being used to address them, we point out certain potential research direction. In terms of technique, we observe that traditional and deep learning based approaches have complementary advantages and disadvantages. Therefore, we advise the use of the two approaches simultaneously. The field can also benefit from new research that combines completion with assistive tasks like upsampling, segmentation, and object classification. In terms of datasets, we are yet to see completion results for dense real-world point cloud datasets and datasets from different sources, such as the subsea environment, and of dynamic object scans captured under harsh conditions. And in terms of architecture, there is a growing interest in the use of generative diffusion models for completion. Last but not least, we believe that human-in-the-loop approaches that incorporate human perception of 3D objects to point cloud completion process could be beneficial. This presentation is only a brief introduction of the survey paper. For details, please refer to the survey paper by using the link in the description. Thanks for watching and have a nice day.